one of the key words in this coming conference on spatial structures is inspiring the next generation. And I will show you, for the start, a couple of very early inspirations I had without knowing it, that I was going to work in this area. No? You see the date of this slide is about 1957. I must have been about 6 years old. And this church, it was designed by Felix Candela. And that's very close to the place I lived about 24 years of my life. And I remember my mother used to take me to this church about every Sunday. So I had the chance to look at this church very quickly from the inside for about 5 to 6 years. And I was enchanted by this splendid design of Felix Candela. Some 10 years later, I came across this book at the top on the right-hand side. That's the Wizard of the Dome. That's the Spanish version of the book about the geodesic domes of Buckminster Fuller. And that's when I decided I want to do this. I want to work on this area. No? More or less at the same time that this beautiful dome down on the left, designed by Felix Candela, Castañeda, and Perry for the Olympic Games in Mexico, also was a very clean and splendid example of a very advanced type of structures. That was a grillage of circular, double chord circular arches, and in between the infills were realized in this Castaño triodetic single layer reticulated hypars. And that's what decided my way into the architecture and design of these structures. I was very interested in geometry and shapes. I also wanted to learn about the engineering of it, but geometry is what pulled me to this, into the field of architecture. And that's when I would like to focus in this middle part of the interview in the geometry behind the spatial structures. And being a geometry designer, I would almost say spatial structures are equal to geometry. Of course, I know this is an oversimplification, and some engineers would say, what about structural analysis? What about materials and some other things? No? But I think one of the cores or the basis of any spatial structure is geometry. I will go through the small or the short review of geometry, or the geometry of spatial structures. Here we have regular space structures, and many of these regular space structures, they have very simple normative principles or principles of growing. For instance, Merrill based some of his norm space structures on this geometric series based on the square root of 2, because that gave a lot of regularity and a lot of combinations having a minimum number of components. The picture at the bottom shows a pedestrian bridge built at the beginning of the 40s, built with norm components. And from that time, and for the next 80 years, many people have been building space structures with these norm components. By the 1980s, this is the collection of components of the Merrill system. There were very small nodes and also very big nodes, very small bars, very large sections. So you could combine it to design and generate small structures, middle-sized structures, and large structures. If you connect these elements, they look like that. Many people are familiar with this type of connection of space structures. Merrill is the archetypical space structure systems. For many years, there were many copies or clones of this system all around the world. The spherical node and the round tube. With this, one characteristic of these regular space structures is that the angles at the nodes are fixed angles, are fixed values, so they can be produced in series, and you can build and design many types of configurations. And that was done through the 60s, the 70s, and by the 80s, well, the structures also started to get more complex configuration, more interesting from the morphological point of view. And many people were designing around the world with these components. of regular space structures. Also, spans kept on growing. By the 80s, we were building, or Mero was building spans as a standard subject of 100 meters, and also the combinations of plate-like space structures like this National Theatre in Kuala Lumpur were done with regular space structures. Even looking into the future, populating 3D space with just a few components offers you an infinite possibilities of building interesting space configurations. This is an exercise we did in connection with Professor Michael Bird of the Technion in Haifa. He started his research in the 60s, and we also tried to apply his ideas for real structures. In this case, we are taking a slice of this infinite polyhedral lattice, see a 6-layer system, and make a comparison with a conventional steel truss system. And from the difference in weights, here 102 and 168, yes, only 68 kilograms per square meters, by a span of almost 300 meters, you see it's about 30% savings with this ultralight space structure configurations. And this is a very regular system. And summarizing the regular space structures, the more regular, the better. The target has been to obtain the minimum number of line lengths of node types, angle combinations at the nodes, on panel types. On the left-hand side, you see here some well-known space structures configurations. In the top row, in the middle, you see the square on offset squares 2-layer grid. And I mentioned this because I think more than 80% of the space structures, regular space structures in the world, have been built with this geometry. Later you will see why. But if you want to map or build space structures on curved surfaces, in this case the cylinder, the first thing you have to do is to liberate the node from the fixed drilling angles at the nodes, so that you can adapt a topological network to any kind of surface. By the end of the 70s, Mero was so far that it had already automated greatly its production and technical processing. We were going parametric already. We were doing automatic dimension of tubes and nodes, including the interference check, the parts list generation, the generation of data sets for NC machining and drilling, and automatic generation assembly drawings. And by the middle, and this is a breakthrough project, this split stadium from 1979 with 213 meters span. And by the middle of the 80s, this kind of large structures, complex structures, as this hyper down on the right from Felix Candela, they were a matter of routine for Mero for the spherical node and round tube system. With almost this system, Mero built a lot of domes. One of the outstanding domes, you know it in the UK very well, is the Eden project in Cornwall. That was a Millennium project, no? And as you can see on the top picture, it consists of 2 sets of 4 interconnected geodesic domes. In this project, it was the first time that the hex 3 hex grid was applied on an icosahedral system. The architect had designed the envelope of these domes with hexagonal networks. But after a feasibility study, we found out, together with Anthony Hunt, the structural engineer, that the more efficient way of building these huge domes was a double layer system. And we found a geometry that has this hexagonal grid on the surface and a semi-regular bottom core layer of triangles and hexagons to stabilize the whole system. You see the largest dome is very large, it's 120 meters in diameter. The largest hexagonal cushion has 70 square meters. That's like a dwelling almost. Also, new requirements require also sometimes new nodes, like the one here on the bottom left, and this provides more stiffness to the connection. Up to here, Mero had designed a lot of structures on spherical surfaces. Most of them were analytical surfaces. But at these times, also the architects were designing free-form surfaces. And of course, current free-form design, it welcomes the rationalization approach of minimizing node lines and mesh types. And this is a feature which is actually nice to have, but it's not essential nowadays due to all the advances done in digitalization of the design and the production. But it's nice to have if you have just a few components. Current freeform designs aims more at satisfying formal intentions, interesting forms, formal expression, and eventually also satisfies structural and architectural requirements. The next project is the Esplanade freeform halls for the Art Center in Singapore. That was the first very large project on freeform project for Merrill. And we were also trying to keep on with the technology and trying also to make the systems more elegant. In this case, here above on the right-hand side, you see that a view from the internal foyer. And here what the company needs to integrate the structure, the two-layer space frame with the glazing and the aluminum sunshades in one integral system for roofing. Down on the left, you see the finished product. By the way, the length of these halls are about 120 meters, 60 meter wide and 25 high. Top on the left, you see our raw material. That's what the architects and the engineers gave us to develop the two-layer structural grid. At that time, we were also systematizing all possible features. The systems were getting more and more complex and larger. So we, for instance, in this case, we generated the whole on the bottom chord and the diagonals with a program based on the duality principle. On the right-hand side, you will see a mock-up of the resulting geometry. The basic grid had a constant length of 1.5 meters and a structural length of 19 centimeters. In this area, or a stage of development of tools development, that was about the year 2000, we also started to extend the geometry model with other attributes, like in this case, for instance, point colors and point symbols. In this way, we could group the nodes of the surface of these holes and create this patchwork. This patchwork is a map of the pressure coefficients of winds for a certain wind direction. And with this approach, we could implement the automatic generation on wind loads for these two holes for 12 wind directions for every node. And that's in an automatic way that fed the structural analysis program. And from the construction point of view, also around this year 2000, we started to use normal vectors at grid nodes, normal to the current surface, and normal vectors at the middle of the lines, with the purpose of positioning and orienting the construction components. In particular, normal vectors at the nodes were used to make offsets of the nodes to create the subsistence of the complete roofing system. The top chord was offset to generate the glazing grid, and with a further offset, the secondary grid for the sunshade substructure was generated. Nowadays, I think these are some sort of standard features to design and construct these free-form space structures. Other designers were going in another way. Here, Maximiliano Fuchsas, year 2004, developed this free-form, very long, 1.3 kilometers, which for construction reasons had to be divided in 12 segments of about 80 to 100 meters. The width varying from 40 to 30 meters and the height from 0 to 16 to 25 meters. And almost half of the surface of this front surface is flat. So we had to re-engineer these flat surfaces to obtain, to get low high pass. And the drainage was done at the low points of these low high pass. Also, these flat areas require bending stiffness. The sections has to be high, so Mero developed this double load to cope with this structural requirement. Other architects were looking at the limits, how far or how big can a space structure be, and Binoy designed this extraordinary large envelope for a leisure park in Abu Dhabi. Up the virtual image of the architect and down the materialized roof. 100 meters, the hole in the middle, 650 meters, the distance between the two corners of this roof. We were always reaching the limits of many programs. Many programs had to be extended to cope with this huge amount of information to be able to do the structural analysis and also to implement the construction. Even renderings, we had a rendering like here, well, it required many hours to be calculated. There are some numbers, we'll skip them. I just want to show that the roof has 200,000 square meters of roof surface, more than 32,000 spherical nodes, and more than 125,000 round tubes. And the whole process of design up to the last stage of construction took only 1.5 years. One aspect that we hear nowadays concerning freeforms is the optimization of networks. But is it possible? Well, I make an oversimplification again. No, if the structure is going to be built, especially if you have a very strong interaction with other architectural elements, like in the case of this splendid design by Zaha Hadid. One important requirement of this design was how the paths of the cladding seams outside and inside running parallel to a certain direction to suggest the flow movement and smoothness. But how do you support these skins? There was, of course, a period of evaluating structural systems, and at the end, the space structural system, especially this geometry square and offset square in combination with this spherical node and tubular system, won this competition. It was because this geometry with this type of connection allows you to approximate almost any geometric shape. We have an initial length optimization. I won't go into the details because we couldn't apply it to the whole surface because the structural grid of the columns inside, they had another module and they divided the surface into patches. So we could only apply our optimization strategy within these smaller patches, but it was a little bit of more work. Also, the variable distance between external and internal skins and the strong curvature variations didn't allow us to minimize the types of nodes. It was really impossible. The interaction with building volumes, like supports positions in the top, in the lower core, they force you to come with your polylines also going through these fixed points. Also interaction with other structural systems. We were happy that we could weave in between these supports to be able to guarantee the support for the cladding. Also the transition to conventional construction when the space frame system couldn't be applied anymore. Also like in this part of the museum where this point at the bottom is supposed to touch the floor tangentially. But it's a very massive tangential point because it's a support point where a very heavy earthquake loads had to be taken, also wind loads. So there was a certain little contradiction with the architectural design. In the end, we had a complete model of this splendid design, and that was the basis for the structural analysis, the construction detailing, and planning the erection of it. And you see it worked because this is a photograph of the real space structure. Summarizing, Baku is a concealed, supporting, and form-giving free-form space structure. Why do I say that? because when you apply the cladding, you don't see the structure anymore at all. Anybody who doesn't know anything about structures and cones, he has not a clue of how these skins are supported. It's another way of using space structures as form-giving systems and as supporting invisible skeletons. We had to keep also developing with the design trends, so we also engage in generative, algorithmic, and parametric modeling. And this is a small example of a facade for the building of the oil company in Norway, in Oslo. And this is a grasshopper script for the people who work with this. That's an addition to Rhino, which is a program for modeling and designing free forms. In this case, you only give 4 points in the model space and the subdivision numbers in the two directions, and it delivers you this structure. We extended this grasshopper formulation to generate the sections oriented properly to the surface. And so in the form finding stage, we could generate very quickly how the structure could be seen. But in the end, this is the resultant structure. And here one word about geometry rationalization. The initial surface of the facades were minimal surfaces, but the panels were not flat. And the architect wanted to cover it with flat panels of glass. So we were lucky, so we compared this minimal surface with a translation surface generated as a hyper generated as a translation surface. It was very, very close to the original design. So we replaced it, and in the end we got glass panels which are completely planar. And my last example here is the Kazakhstan pavilion for the Expo 2017 in Astana. That's a sphere of 80 meters in diameter with spherically curved glazing. This is the geometry definition from the architect. He took a sinusoidal meridian and it rotated it to 80 times above the sphere vertical axis to generate the glazing grid. And that was the definition. But for construction and economic purposes and fabricational purposes, we had to rationalize or simplify this geometry for production. What we did, we took divided the freeform meridian in segments, more or less every 9 meters at every floor. We took the two end points of a segment and the middle point, and with this we define an arc, a circular segment. The great advantage of this is that the secondary structure is built with round tubes which are bended, and it's much easier to bend a plane line with a constant circle on a plane precisely. We played a little bit around with the form, and from the center, perpendicular to the base of the cylinder, we extended the line and we met the sphere center. And we proved that, we tested that for the other segments, and all the cones axes landed in the center of sphere. And that had a very nice consequence. All these conical segments, which are neighbors, they have a tangential condition at the common line in between. And the consequence for the constructions, when you have a multi-layer system of glass and secondary structures and fixings, is that every edge of this section, when it goes from cone to cone, there's no jump in between. All these lines go continuously from bottom to top with no torsion and jumps or twists. And that was a great gain, a great simplification for the construction. This is a rationalized meridian and also the basic segment for the secondary structure and the glazing. This is the end product, spherical or spherically curved glass. Special structures, equal geometry, okay? So I'm back again.